Okay, so this last hour of lecture will be mostly about things that are not differential geometry. And I will be, given the subject, I will be not completely precise about everything. It will be an approximation of the truth. So we start by talking about Monte Carlo methods. Probably you know what a Monte Carlo method is, but more or less it's a way to compute integrals or series by drawing random samples from a suitable probability distribution. From the probability or statistics viewpoint, it is a mean to obtain estimates on probabilities or mean values, expectations, or parameters of our distribution. The main, the easy example is the approximation of an integral on 0, 1 by the average of the values of your function in n independent randomly sampled points from the uniform distribution, because the Lebesgue measure we are integrating in is the uniform distribution on 0, 1. Obviously, there are, there are problems in this setting, which, you can do a lot here, but there are problems. First of all, it's not always easy to draw independent samples from a distribution, particularly if the distribution is not a easy distribution. It's not like the uniform distribution or a normal distribution, even a multivariate normal distribution, but it's a real-life thing, so something coming from a real-life problem. At that point, sampling from the distribution is not easy at all, and also drawing independent samples, it's not easy. On the other hand, it's not always convenient to draw independent samples. For example, the main, one of the main ways to approximate the distribution is to draw samples from another easy distribution and then accept or reject the sample depending on the value of the distribution we want to approximate. I am being sloppy on purpose here, but anyway, the idea is that, let's say we have some density, something like this, on some interval 0, 1, let's say. And this is our density distribution, or even just some probability density function, even not normalized. So what do? We pick random points in 0, 1, uniformly random points, and then we accept or reject them depending on our distribution. Let's give it a name to this, h of x. So the point is that, there is a practical algorithm for each random draw to say if it is okay or not to keep it in order to approximate h. We are not going into that, but you can imagine that we would like to have more samples here than maybe here or here. Whereas for the uniform distribution, the red and the yellow, the orange part are more or less the same. So that means that we will be drawing a lot of samples that we will reject because they are in places where our density doesn't have a high concentration. Moreover, let's say at some point we have a sample here, and we notice that there is a moderately high value of our density distribution function at that point. We would like to find the next samples nearby. But this is exactly the opposite of saying that we would like to draw independent samples, in a way. So independent is a problem in two directions. One, because, well, we know everything. I mean, we know a lot about independent random variables. And on the other hand, so we have the central limit theorem, the large numbers theorem, etc. On the other hand, maybe it's not that convenient to really have independent samples, because we would like them not to be independent in order to efficiently approximate our age. So Markov chains, that's the tweak that's added usually to the Monte Carlo algorithm in order to overcome this difficulty. In general, if your random variables are not independently distributed, you lose a lot of information, but in some kinds of situations, like when they are part of a stochastic process where you have some other features, you can still say something. And one of these cases, the most famous one probably, is the Markov chains. So in round terms, a Markov chain is a random walk. So you're moving randomly with some probability, transition probability between states, between places, between points. So we are given a set of states, finite or infinite, for example, all real numbers, and a sequence of random variables taking values in the set of states, x1, x2, etc., such that, okay, what does this mean? So this means that the conditional probability of the n plus 1th step with respect to the past, to everything that happened before. Oh, here is an n, not an m. So the conditional probability of the n plus 1th step with respect to all the previous ones is equal to the conditional probability of the n plus 1 step with respect to the previous one. So that means that each step depends only on the previous one. Now, if the state space, so the set of states, is not countable, for example, the real line, this is not the right way to formulate things, but the right formulation is anyway, I mean, is the same idea, just you have to write it down in a different way. But the core idea is the same. The idea is that the next step you take depends only on where you are at this moment. So it doesn't depend on the past, just only on the present state. Now, these random variables have some probability densities, some probability distributions. So if you, how do you change from one to the next? Well, with the conditional probability formula. So if you have the conditional probability distributions, which in a way is from x of x2 known x1. So in a way is the probability from going to from x1 to x2. And G is the marginal distribution of the random variable x1. Then the marginal distribution of the random variable x2 will be the integral of f g in the x1. if G tilde is equal to G, then G is what is called the invariant distribution for the Markov chain. In a way, what is an invariant distribution? A random variable of our Markov chain X has as its marginal distribution an invariant distribution if the probability of having at that point of the Markov chain some value is the same as the probability of having that same point onwards in the Markov chain. Under reasonable assumption, it's not always true, but under reasonable assumption, Markov chains tend to their invariant distribution. Or distributions, but again, under reasonable assumption, this distribution is unique. By the way, if you are, and we won't, but if you are in the finite case, so if you have a finite number of states, everything boils down to matrices and vectors, and you are solving an eigenvector problem, a left eigenvector problem. Well, it's technicality. So you have your matrix of transition probabilities, and you're trying to find an eigenvector of eigenvalue 1 of your transition matrix. It's a nice, probably a nice way to understand what's actually happening, because it's a way of building examples. However, it would not fit in this discussion, so sorry, I won't be giving that example. Anyway, the idea is that you have a way to transition from one step to the next in the Markov chain, and an invariant distribution is, in a way, what reasonable Markov chains tend to after a number of steps, which is a distribution which is left invariant by the Markov process. Now, if you put Markov chains and Monte Carlo method together, you get what is usually called MCMC, Markov chain Monte Carlo, which is a Monte Carlo method where the successive draws are not independently drawn, but are the steps of a Markov chain. So we are not anymore saying that at each time we, for example, take a random number with uniform distribution and then accept or reject it, but we take a step in a Markov chain. What's the whole point of this? The Markov chain should be, otherwise it will be useless, should be carefully designed so that its invariant distribution is unique, so that it tends to the invariant distribution. This invariant distribution is unique and is the distribution that we want to sample from. So, for example, if the Markov chain is positive recurrent, you have that the invariant distribution is unique and equivalent of the law of large numbers holds, and so the Markov chain tends to its unique invariant distribution. Now, the whole problem is to build a Markov chain that gives you as invariant distribution the distribution you want to sample from. Obviously, the Markov chain has to start somewhere, and depending on where you start, you will get a first part of this chain of these samples which are useless. They don't really have anything to do with your distribution. This is sometimes called the burn-in stage or phase. Then at some point it starts working. You can estimate the point, obviously. It starts working, and then it starts being a good approximation of your distribution. There are ways to estimate this time. And obviously, if you take, if this time is really small with respect to the number of steps you take, you can get rid of the burn-in stage or not. At that point, it doesn't really matter. Now, how to build this Markov chain? So one way is the Metropolis or Metropolis Hastings random walk. We have H, the density distribution we want to sample from. H doesn't have to be really the density distribution. It could be also a multiple of the density distribution, just an unnormalized. So that the integral, it has to be with a finite integral. It has to be positive and with a finite integral, but not with integral 1. It's not important here. So start at a point where your density is positive. Generate a displacement vector from a normal distribution with mean 0 and some variance, sigma squared. Now compute the ratio between the new value of h at x plus y over the old value of h at x. Now here you obviously need that the starting point was a point with positive density. Now we generate a uniform random variable on 0, 1. You take a sample of that. And if this sample is, well, less than or equal or even less than r, you reassign x as x plus y. And then you return x. Now, miraculously, it works. It gives you this gives you a Markov chain, a random process that converges, that is positive recurrent, and converges to the probability distribution given by h as a probability density function. Obviously, it can happen that this process stays constant for a number of steps, for example, because if you keep drawing y's that give you a too small r, then maybe, so for example, you are in a point where h is quite large, and you draw some y which is too far. So h will decrease, and if decreases too much, it will give you a very small r, so the probability of being accepted is very low. It's r, so it's very low. So we'll stay in that point for a long time. This is the opposite of what it happens with the Markov, with the Monte Carlo method, because the Monte Carlo method draws independent samples, so they move independently. Here, they can stay in the same place for long time, or at least any number of steps. So this is actually the Metropolis random walk. The Hastings variation is using a displacement y which is not normally distributed. Why doing that? Well, so let's say you're at a point x, and let's say we are on the real line. These all could be random vectors, but let's stay in R. And you have your Gaussian displacement, and you select a new point. Let's say you go to xn plus 1. Now you will have a new Gaussian displacement here. Now, the probability, I mean, the probability of transitioning from xn to xn plus 1 is related to where the Gaussian around xn plus 1 hits on xn, around xn hits on xn plus 1. The other way around, the probability of going back to xn is exactly the same, because these two Gaussians have the same sigma squared. So they are symmetric. And this is the metropolis version. So you have the same probability that brought you from xn to xn plus 1 to go back to xn. And this is, I mean, you don't really want to be stuck in the same place usually with these algorithms. I mean, once you move, you don't want to just loop or do things like that. So you want to avoid something like this. And the usual solution, I mean the Hastings solution, was to use a distribution like this. So something which is not symmetric. I mean, this is just one of the possible variations. Now, sigma squared. Sigma squared is the same, but has to be tuned, because sigma squared is the scale on which we are working with our algorithm. So sigma squared is the variance of the displacement we use every time. Now, if sigma squared is very small, we will be moving with really small steps. Obviously, this will imply that you have, I mean, sigma squared small or large. Obviously, there is a, I mean, it's not a dichotomy, you can be in between, but here you have easy acceptance. So almost every time you try it, you move it. You move on your Markov chain. So every time you try to move, you actually move, because I mean, you're taking small steps. So that means that h of x plus y will be very, very close to h of x. So this will be very, very close to 1. Okay? But small steps. And if you think about it, if you want to sample from a distribution, it means you want to travel the whole space where this distribution is defined. Otherwise, you're only sampling from a region, so the restriction of your density function to some part, and you don't want that. You want to travel the whole space. You want to be ergodic. But anyway, if sigma squared is large, you're taking big steps. But you're having a hard time of getting acceptance. So, I mean, it's not obvious. It has to be tuned, and there are a number of algorithms that tune this sigma squared along the algorithms. They change it automatically depending on some other things. You can, I mean, the history of your process in a way, or the values of H register or whatever. Otherwise, it has to be tuned by hand, experimentally. Sorry. By the way, we don't want an acceptance rate of 1. I mean, we don't want to accept everything with probability 1, because that means either that H is very stupid, constant, or that we are taking really, really small steps. So we actually want some balance. I mean, I think in the literature the nice value is around 2/3, so 0.66 or something like that for this R. So that means that you're working well, at least. Literature says so. And acceptance probability, I mean, also the way we define acceptance probability was a very naive one. There are other ways to define it, which are more or less, equivalent, but, related, but not exactly the same. Now, a step towards the subjects we have been dealing with in the last lectures, Hamiltonian Monte Carlo. So, why? Well, the main reason is to, in a sense, avoid random walks. So we don't, random walks, like the Metropolis Hastings random walk, are a good tool to produce Markov chains for the Monte Carlo method, but they have some intrinsic limitations in how they visit the parameter space, so the space where your, the domain of your functions of your densities. One solution is to use Hamiltonian dynamics to produce the next step in the Markov chain. So you're actually using a sort of gradient flow. You're using a vector, the flow of vector field, the Hamiltonian vector field, to produce the next step in the Markov chain. Now, you can actually, once you write it down, you have to write down Hamiltonian. So the usual Hamiltonian is this one. You have this part is a kinetic energy term. So it's, if you remember from the previous lectures, this part is what you get when you take the Hamiltonian of a free particle. So you have just something which is moving according to, according to its kinetic energy. You just, the Lagrangian is 1/2 is the kinetic energy. The Hamiltonian is again the kinetic energy, just this is the momentum and not the velocity. Plus, or actually minus, because it's negative, a potential term, which is the logarithm of your density function. Why? Well, because, if you think about it, the logarithm of a density function has a minimum where the density function is bigger. So this potential makes the dynamics go toward the areas where H is bigger, so the distribution is most concentrated. So what's the scheme of the algorithm? You draw a random sample from the normal distribution of mean 0 and variance sigma squared to update alpha to alpha star. So we start from a point x alpha, and we randomly move alpha, because we are not interested in alpha. In the end, we will be interested only in the x part, because the x part is the part where our probability density is. So we will be getting samples of x. Alpha is a auxiliary variable. So we update alpha to alpha star, which is a new value of alpha, which is shifted by some random vector. We simulate the Hamiltonian dynamics from there to obtain the update for x and obviously also for alpha. So we have x alpha. We go to x alpha star with a random draw from the normal distribution, and then we simulate the Hamiltonian dynamics. So we follow the Hamiltonian vector field for a while, for a number of small steps, usually. And we obtain an update for x. So we obtain x prime, alpha prime, which are the new points of our system. Ha. This is very nice. Okay, let's wait a second. So we accept or reject with probability beta, which is the minimum, obviously, between 1 and the comparison between these two exponentials. Why the exponential? Well, because this makes sense if you ever studied like statistical mechanics or stuff like that. But in a way, the Hamiltonian is the logarithm of the joint probability between x and alpha. So we have the density function h on the x part and a Gaussian density on alpha with variance sigma squared and mean 0. So when we take the exponential of minus h, we're actually comparing the two probability distributions, the joint probability distributions between x and the x variables and the alpha variables. Now, what are we comparing here? We're comparing the new value at x prime, alpha prime, with the value after the update of alpha. So here is x alpha star. So from this point to this point, we only ran the Hamiltonian dynamics. Now, why we would like to use Hamiltonian dynamics for this? It's a nice idea. It's a very funny idea mathematically, but does it work? There are a number of features of the Hamiltonian dynamics that are relevant to this kind of algorithm. So the reversibility of the Hamiltonian dynamics. Hamiltonian dynamics is the flow of a vector field on the cotangent bundle, but it's the flow of the vector field. So if you remember, the flow of a vector field is given by diffeomorphisms. And so first of all, you can always go from time t to time t plus s by applying the same transformation regarding of t. So it does not depend on t. It only depends on how much forward you want to go. And obviously you can go backwards just by using the minus s flow. So it's always reversible. The second feature is h preservation. So when you run the Hamiltonian dynamics, the Hamiltonian function is preserved. You are moving on the levels of the Hamiltonian function. Now, this can be seen in various ways. Well, if you think about the formula of the Hamiltonian, in a sense, in the Euclidean case, it's clearly perpendicular to the gradient. This is not a proof for a manifold, but yeah, that works too. Suppose you have a trajectory of your Hamiltonian system, and you take the derivative of the Hamiltonian in time. Now, what you get? You get well, let's say we have n variables. So we get the derivative of each spatial variable with respect to t times the partial derivative of h with respect to xi plus derivative of the momentum variable with respect to t times the partial derivative of h. Now, the Hamiltonian equations tell you that dxi in dt is equal to dh in the alpha e, and that the alpha e in dt is equal, the alpha I in dt is equal to minus partial h over partial xi. So if you plug these two in, you get 0. So the time derivative of the Hamiltonian is 0, so as long as these two equations hold. And these two equations are the equations for the Hamiltonian dynamics. So as long as we are simulating the Hamiltonian dynamics, the Hamiltonian is constant. Now, another feature is volume preservation. Now, volume preservation, what does that mean? It means that if you take a small ball of points, actually any set of points, and you move them in your Hamiltonian dynamics for a given time, the volume of the initial set and the volume of the final set are the same. This is called Liouville theorem. And I'm not talking just about the positions, I'm talking about the volume inside the X alpha space, so inside the whole cotangent bundle. The main idea is that well, I mean, if you know it, you can notice that the divergence of the Hamiltonian vector field is 0, and a 0 divergence vector field preserves the volumes. Or you can write down an approximation for the Jacobian matrix of the transformation and see that the determinant is actually 1. The modulus of the determinant is 1. Why are we interested in I mean, let's talk about it later. The fourth property is symplecticness. So it does not only preserve volumes, it preserves the symplectic matrix that we talked about. And the fifth property is ergodicity, meaning that it visits everywhere in a sense. I mean, the whole algorithm, also with the update, the normal random update in alpha, obviously. Now, why are these features interesting? Well, the first the reversibility feature helps us saying that the Markov chain transitions are reversible, which in turn means that, I mean, we can prove that the Markov chain leaves the desired distribution invariant. So the fact that the process obtained from the Hamiltonian dynamics is reversible means that the Markov chain is reversible. That means, and that gives out a very easy way to prove that the density, the distribution given by the density H is left invariant by the Markov chain, and so that it will be the density distribution that we tend to. Why do we care about H preservation? Well, if you remember, the acceptance probability was the minimum between 1 and this ratio. And this ratio is between two values of, well, the exponentials of two values of H at 2 points, which are obtained one from the other via the Hamiltonian dynamics. So if this is simulated exactly, which is impossible because it's a simulation, but if we were able to run the Hamiltonian dynamics exactly, this would be 1 always. And volume preservation has to do with something I won't be explaining, which is called detailed balance, which is a property of Markov chains that is useful in, which is needed in the Markov chain Monte Carlo. Now, this is an interesting aspect. How to simulate Hamiltonian dynamics. So we cannot just analytically solve the Hamiltonian differential equations. It's almost always impossible. So we need an algorithm to simulate it. If you try and use like, Euler algorithm or something like that, you run into problems because that approximation is not volume preserving anymore. And this gives you Hamiltonian, this gives you trajectories that, obviously at first are close to the Hamiltonian system, but after a number of steps diverge. The right algorithm is what is called Leapfrog algorithm, which is something that approximately preserves volume and H. Not exactly, so we won't get beta equal to 1, but approximately, and so it's good enough. Now, the first step is to update, so we want to simulate the Hamiltonian dynamics. So alpha updates with the partial derivative in x, with minus the partial derivative in x of the Hamiltonian. Now, we calculate alpha at time t plus epsilon half, and this will be alpha at time t minus epsilon half, the vector, the gradient vector of h with respect to x. The second step is to get x at time t plus epsilon, and not epsilon halves, which is, okay, today is the day of LaTeX errors, which is x of t, so the previous value, plus an update, which is epsilon times the alpha derivatives of h, not at alpha t, but at alpha t plus epsilon halves, which we computed before. And then we update completely also alpha using, okay, was saying, and now we update also alpha from alpha t plus epsilon halves to alpha t plus epsilon using epsilon half the x derivative of h at xt plus epsilon. So, if you try and draw it, it's not a, you're not going linearly through the times, that you're jumping left and right, so this is why it's called leapfrog algorithm. You can prove that this algorithm preserves the volume because, in fact, because these transformations use at first order shears, which are volume preserving linear transformations. So in the end, it approximately preserves volume, which is what you need. Now, the last step, Riemannian Monte Carlo. Now, in Bayesian statistics, I mean, there is this eternal war in statistics between frequentists and Bayesian. But in Bayesian statistics, the object of interest, the random object, is the parameter of the distribution. So the mean, the variance, whatever. So usually you are your target probability is on a parameter space. So for each point, you actually define a probability distribution with that parameter. So your X moves on a statistical manifold with its Fisher metric that we talked about. The kinetic energy part of the Hamiltonian, so the sigma squared halves norm of alpha squared, may be written using the inverse Fisher metric. So you end up with something looking like this. So minus log of your density plus 1/2. This is just the norm of alpha with respect to the inverse metric. And this is the normalization constant, because this won't be getting you a probability distribution in general. You have to divide by the integral, which is this thing. C is a dimensional constant, so it depends just on the dimension. It's 2 pi to the n or something like that. So now, this is the Riemannian manifold Hamiltonian Monte Carlo, so RMHMC. That's the usual approximation. Why is this useful? First, Leapfrog algorithm doesn't work anymore here, because there is another term with this weird stuff here. But anyway, why is this useful? You get a close relationship between the geodesics in the Riemannian manifold of probability distribution and your steps in the Markov chain. And this means you can more efficiently move on your manifold of probability distributions. And you have, you get faster and more efficiently to the regions of high probability. So the samples you draw are more significant. And it generally works better. Obviously, to modify the interpolation algorithm, so the Leapfrog algorithm, and to understand why everything is working out, you not only need to know the differential geometry and the Riemannian geometry of the manifold, you also need to understand what you're doing from a statistical viewpoint, because this G, in a way, is it can be interpreted as a kernel matrix or a covariance matrix in some Gaussian distribution, which can be estimated in other frequentist ways. So, there are relations between the objects, but everything miraculously works out. So anyway, this is the Riemannian Monte Carlo method, which is quite commonly used in Bayesian machine learning and stuff like that. And I think this is more than enough, and I will stop here.